So where we're going to start is looking at our KSP. Okay, and I hopefully, maybe, oh, come on, please work. What we mentioned is we look at a particular substance. I'm going to pick silver chloride as an example here. Silver chloride is typically insoluble, but since this is 152, we acknowledge that solubility is a spectrum and that it could dissolve a little bit. Okay? And if it dissolves a little bit, what we're going to see is our silver ion and our chloride ion aqueous. And this is our dissolving process. We end up flipping it in regards to solubility instead of looking at it as we did in kind of the 151 expression. Which means when we go through and write out our K expression, it's just going to be our silver ion times our chloride ion, which is now talking about solubility because we're looking at the solid dissolving into the aqueous environment. So that's our S for our KS. And then the P is product because what are we doing mathematically? We're taking a product of our two reactants, our two products. Okay, so we're getting our KSP. The larger the KSP, the more soluble the compound is. Why might that be the case? If we get a bigger KSP, that means I have more silver ion, I have more of the aqueous species, which means more stuff dissolved. That's kind of how that correlates. So we can look at kind of the magnitudes of different KSPs. A KSP that is greater than 1 is something that is typically considered soluble. A KSP less than 1 is typically considered insoluble. Insoluble meaning that it doesn't dissolve. That's our silver chloride as an example. Okay, so we've got a whole bunch of different types of ionic compounds listed out, and if we go through and look at all their KSPs, they're all less than 1, which means all of these compounds, if we went back to our 151 rules on solubility, we would see that all of these products or all of these compounds were insoluble. And because they were insoluble, we could say that a chemical reaction happened when we mixed their individual ions. Okay, which sets us up with our first blue question. Which compound with carbonate is the most soluble? Which one is the least soluble? Okay, officially, you don't need to know what carbonate is as far as nomenclature goes. At least we have a slide talking about that. So the carbonate is CO3 minus 2 in and of its own, which means we can ignore the top and bottom of our table. So now at your table, decide which carbonate is the most soluble, which is the least. So this gets fun because we're dealing with negative powers of 10, so we have to make sure we're understanding and interpreting our numbers correctly as we navigate this. If we're looking for the compound that is the most soluble, we're looking for the KSP that is the biggest. Okay? Most soluble should be our biggest KSP, and our least soluble should be the smallest KSP. So if we're going to go through and look at these, hopefully where, or at least what I've got starred, are places where people kind of triggered off of trying to recognize these things. If we're looking at the biggest KSP, where would we start evaluating our numbers? Should we look at the scientific part of it, or should we look at the power of 10 part of it? The power of 10, that's going to be our first approximation that we should want to jump to. So if we're looking at the biggest value, why did you not look at, say, well, I mean, we could make the argument that you didn't. Are we saying 13? That's the biggest number there, right? Is that right? No? Okay, why not? Why is it the smallest? 13 is bigger than 11. Is negative. That negative sign comes back and haunts us. We have to watch out for that. Okay, so if we're looking at the biggest value, we're going to want the smallest negative value, which is going to place us at that 10 to the negative 5, and that's the biggest one we've got, right? So the magnesium carbonate should be our biggest one. Because it's the biggest, that one is the most soluble. right? If we now go through and look for the least soluble, we can flip that, and now we want to look for the biggest negative value. Okay, and as we flip through the biggest negative values, hopefully we note that there's 2 negative 13s. Which then sets us up with the next question, because those are the same magnitude. We now have to deal with the quote-unquote scientific part of it, and we need to look at the 1.5 and the 8.0. How do we go through and evaluate that? What's that? Whichever one is smaller, which means? Our PbCO3 is smaller. Everyone okay? Make sense? Okay. Again, we do have this issue with the numbers kind of in front, messing with our interpretation, so we got to make sure we're clear as we navigate those. That 8 is closer to rolling over and making it tend to the negative 12th. Does that make sense? Okay. So that's dealing with our KSP in kind of the general magnitude sense, which then means we can, of course, advance on. We want to write a chemical expression, including the states of matter, and a KSP expression for each of the ionic compounds dissolving in water. Okay? This caused a little bit of struggle with whatever yesterday was. So we'll go through and do the first one together. Right? We're starting with the compound dissolving in water, which means what phase should our MgCl2 be? Solid. We're dissolving it with water, which means we're doing a quote-unquote reaction with liquid water. What's that then going to produce? Well, our ionic compound should dissociate into the individual ions. That's what's happening when we dissolve salt compounds. So what are the ions? Mg, I'll give you most of the credit. That's not technically an ion. How do I know it's an ion? It has to have a charge. What is the charge for magnesium? +2. Should you know that? I would argue that's something that you should have memorized. Right? Dealing with our charges, our common ionic charges for certain metals. Those metals are things that you should know the charges for. Magnesium is in the group 2. All metals in that column are a +2. Right? What's the phase going to be? Aqueous, because we're saying it dissolved in the water. So we'll specify the AQ afterwards. What's the next ion? Okay. The next ion is chloride. Right? What is the formula for our chloride ion? Cl with a -1. That is the charge for our chloride. Again, that is something that you should have memorized back in Gen Chem. It's in that halogen column. Our halogen column are all going to be a -1 in an ionic compound. So we're looking at Cl-. Okay, we do have a little bit of a dilemma here because this shows a 2. What is the meaning of that 2? That 2 means there are 2 chlorides to balance out the magnesium. So that when I go through and split it into the ions, what am I going to get? I'm going to get chloride ion, but I'm going to get 2 of them. Again, aqueous. Some things that we can backtrack through to potentially simplify this. Do you see the water liquid appearing anywhere? Other than in the reactant? Right? Actually, you do. What does AQ mean? Dissolved in water, which means we can effectively ignore the presence of that water in our expression because it's already implied by saying AQ in our products. All right, so that can simplify my chemical reaction. If I was going to write out a KSP, my K equals products. What are the products? Our magnesium ion, cool, concentration of our magnesium ion, and then concentration of our chloride ion. Would we now have our KSP? No, why not?
The Cl would have an exponent of 2.
We need to bring in our coefficient. Okay, remember our K values incorporate the coefficients directly into the expression. Okay, so we don't need to include the MgCl2 as a reactant because it's a solid, and as a solid, once it's there, its concentration is going to remain constant. So as long as it's present at all, its concentration doesn't change, which means it's not going to affect Okay, our K expression. Kind of make sense? Cool. Which means your turn, do the second one. So I've written some stuff up on the screen. What do we think? Is this a proper equation? No, why not? Did we do the exact same thing we did above? So why is it wrong? I just did the exact same thing. One of the things that you're responsible for knowing is that NO3 is a polyatomic ion, which means it stays together. Okay? You don't necessarily need to know that that's nitrate. I would highly encourage you to actually memorize that, but that's a different argument. Okay, so I need to keep that together. So I've got then this, right? And since nitrate's a -1, we can go through and say that. Right? No, why not? Okay, that coefficient, or sorry, that subscript, okay, note, it's in the exact same location that it was with the magnesium chloride, right? And yet we're saying it has a different meaning. Why?
Because there's just 3 oxygens, not 3 nitrogens as well.
Right, sort of tied to that. Why do I have the 2 in the MgCl2? To balance my chloride with the magnesium. Why do I have the 3 in NaNO3?
Balance the oxygen with the nitrogen.
Okay? And that's where we're going to potentially encounter issues. We're saying balancing the oxygen with the nitrogen, which is going to be really problematic because when we're talking about balancing, what are we talking about balancing? How is the chloride balancing the magnesium? What is it balancing against? Our charge. What's the charge on nitrogen? No. Therein lies the dilemma. And I love where you looked. Periodic table, it's definitely a -3. You're right, it is a -3 in an ionic compound. It is not nitrogen in an ionic compound. What is that nitrogen in? A polyatomic ion, which means the charge rule's completely irrelevant. The nitrogen is actually not a -3, it's actually a +5 oxidation state. Okay? And that's because it's a polyatomic ion. So everything kind of falls apart at that point. Okay? How can we avoid dealing with oxidation states, potentially? Well, we could go back and we can change our understanding of what that 3 means. Okay? When I went through to balance the magnesium, what did I write on the product side? Quite literally, what did I write to represent the magnesium? Mg. Why did I not write M, let's say +1, plus G +1? Well, that's stupid, Mike. Why would you do that? The G is what makes it magnesium. They're together. Guess what the 3 is? That 3 is what makes it nitrate. It's part of its symbol. Just like the G is part of magnesium symbol, the NO3 is part of what makes that nitrate. You change that number, it is no longer nitrate. It changes the identity. What becomes dangerous is we're placing that number in the exact same location for a different meaning. This is why it becomes critical to understand what your polyatomic ions are and to have them memorized. Is that the next slide? It's not the next slide. It's close. Okay, so we have to be real careful with making sure we understand that so that when we go through to complete our reaction and we split this into the ions, that 3 is part of nitrate. It's NO3. And as knowing that as part of it, I also know that the charge for the nitrate is a -1. All of that information has to be tied into my backbone, if you will, for interpreting. This is one of the reasons why you'll get instructors saying that you need to memorize certain pieces so that you don't have to try and explain some of these secondary aspects. Kind of make sense? Okay. What happens to my KSP? It's just going to be the concentration of the sodium ion times concentration of the nitrate ion. Ta-da, we have an answer. Curveball hard question. Which KSP is larger? Talk at your tables. Down a little bit. So what do we think? Which one's bigger?
100% K2.
Okay. We're hearing a confident K2. Anybody else think K1?
Can't tell.
Okay. Or a can't tell. Can't tell is a sort of okay argument. I personally would say it's a bad argument. Okay. But within the context of your class, I think you're probably okay with that one. Okay. I frequently heard people saying, well, K1 must be larger because we square the chloride concentration. Okay. So it gets bigger, right? But that's assuming the chloride concentration initially is the same size as any one of those. Because if the chloride concentration is next to nothing, squaring it really isn't going to make it any bigger. Okay? So it has nothing to do with squaring or anything else. It has to do with how much of those ions are actually present. How would you know how much the ions are present?
Solubility.
If you'd memorized your solubility rules, group 1 metals are always soluble, which means
And NaO3 is always
NaNO3 instantly turns into the ions, which means the concentration of your sodium and nitrate is through the roof. You're looking at a KSP that's larger than 1. Okay? You're making the assumption that magnesium chloride is not soluble. Is that a valid assumption? I actually don't know. Okay, I didn't memorize that one. Okay, how would we figure out the magnesium chloride was not soluble?
It is soluble.
Okay, it is soluble. So if it is soluble, really? Was it soluble? That's annoying.
I'm pretty sure.
We could go back to our solubility rules and see magnesium chloride, yeah, it is soluble. Okay? So how would we be able to determine that? Now what we'd have to do is actually get into the values of how soluble they each are, okay, to try and quantify that difference. If we don't know that context, that's okay. But we can leverage our solubility rules to help us kind of make those interpretations. Does that make sense? We can only leverage those rules if we've done what? Memorize them. If you haven't memorized them, then it becomes really hard to manipulate that. Okay? Are you responsible for memorizing them? No, you're not. What we're trying to look at is, are there things that we could do with that knowledge if we had it? Does that make sense?
So if NaNO3 is soluble, would that make it show up in the denominator of the KSP?
When it's soluble, what happens? It turns into the ions, which means the sodium nitrate that I'm adding into it is just immediately turning into the ions. There is no concentration of the sodium nitrate that is, as a whole, aqueous. So it doesn't show up in our denominator at all when we're talking about our solubilities. Okay? So other ways that we could go through and look at this, we look at the structures. This can help us to see what's going on with that NO3. The oxygens are part of that complex ion. They're tied to it so that when I dissociate into the individual ions, I'm seeing those individual pieces. So we have to make sure that we recognize what's happening within that system. Make sense? This is why it becomes really critical that we know our polyatomic ions, or at least know what the formulas are so that we don't make the mistake of dissociating them when they're not supposed to dissociate. Make sense? Okay. My understanding is, again, you're not responsible for the nomenclature. You are responsible for knowing what those formulas are. So if you see PO4 minus 3, you should know that is a complex ion, and that stays together when you navigate through the solubility. You don't need to know that PO4 minus 3 means phosphate. Make sense? Okay. The structures are also provided there. Do you need to know those structures? For the sake of this class, no. When should you have learned about those structures? 151. Okay? That's when that content would have been relevant. Can you draw out those structures based off of 151? 152 doesn't look at those structures. Okay? They're provided here so that you can see the connectivity of what's going on within those ions. Kind of, sort of? Okay. Which then takes us to a new definition. This definition is molar solubility. Okay, so when we're talking about our KSPs, one of the things that we'll tend to want to consider is that if I'm trying to figure out how much ions are present in solution, I have to know how much I've measured. I never measure the copper ion. What I'm going to measure is the copper chloride. Okay? I would get a mass of that. What I'm trying to do is to predict how much of the copper ion or chloride ion would come out of it. So what we have to consider is how do we convert the mass that we're getting, or the moles that we measure out, and turn that into the individual ions. That's our molar solubility. So it's the maximum number of moles of a compound that can be dissolved in 1 liter of water, also known as molarity, okay, which is why we call it molar solubility. Kind of, sort of? So how could we go through and manipulate it? If I want to find out how much of this dissolves, how do I do it? Right, well, it's going to be dependent on my KSP. Well, what was my KSP? And if you tell me 3.4, what is my KSP? Awesome. It's Cu plus times the Cl minus. What I'm doing is leveraging my K expression to tell me what this value is. Okay? If I can determine the copper ion concentration in solution, should I be able to turn that into copper chloride? Said another way, I want to know the copper chloride. Let's rewrite that a little bit prettier. Our moles of copper chloride per liters of our solution. If I told you you had 0.02 moles of copper ion per liter of solution, would you be able to do that conversion? Right? How do we do that conversion? My argument, if you go all the way back to how I teach Chem 130, what has to happen to the units of moles of copper ion? It has to go away. Since it's currently written in the numerator, where should I put it in my conversion? I should put it in the denominator. What do I want to appear? I want my moles of copper chloride to appear. And where do I want them to appear? In the numerator, because that's where it shows up in my answer. So now the question, is there a conversion factor that allows me to relate those two things? Yeah. Where's that conversion factor found? That's the coefficients of, so we got to be kind of careful. That's the coefficients of our balanced chemical equation. Is this equation balanced? Yeah. So we can say 1 and 1. So what's the concentration or the molar solubility of the copper chloride? 0.02. 0.02 moles of copper chloride would dissolve in 1 liter of solution. Okay? But that required that we knew the concentration of the copper ion. I just said what it was. Could we actually figure out what the number was? And I sure hope it's not that same number, because that would be kind of embarrassing. How do we figure that out? No molar masses. When is the K valid? At equilibrium. So what we're talking about is that I'm going to take some mass, unknown mass of the copper chloride, right? And I'm going to add it into solution, and it's going to dissolve. Right? Before it dissolved, how much copper ion did I have? 0. How much chloride? 0. Okay. If I look at that, I don't even need to know what X is, but what do I instantly know is going to happen? What's going to happen to the concentration of copper ion? It's going to increase. What's going to happen to the concentration of chloride ion? It's going to increase. What's going to happen to the concentration of the copper chloride? It's going to decrease. This looks kind of familiar, right? Okay. And if we're talking about molar solubility, how much should the copper chloride decrease? I don't even care about how much it increased on the other side. If I'm talking about molar solubility, why by X? Because that's the definition of molar solubility. It's how much can maximally dissolve. Okay? Since I'm trying to solve what that X value is, this needs to disappear. So that at equilibrium, how much would I have? 0. This seems an awful lot like an initial setting, a change in my conditions, and an equilibrium setting. How much should the copper ion go up if I said it goes down by X for the copper chloride? Why does it go up by X and not 2X or 3X or half X? Because the coefficients from the balanced chemical equation are 1 and 1. Why is this helpful for me? What do I now know? I know my K was 3.4 times 10 to the negative 7th. Do I know my concentration of copper ion? It was X. Do I know my concentration of chloride ion? It was X. Can I solve for X? X is now just going to be this, come on, pen, work with me, the square root of both sides of the equation, and I'm going to get some number. Did you give me a number? Is that what that was?
5.8 times 10 to the negative 4.
Good, it was not 0.002. Okay, what did I say X was? And don't you dare tell me 5.8. What did I say X was? Okay, I said that was my concentration of copper ion. I also said it was my concentration of chloride ion. I also said it was the concentration of copper chloride that dissolved. As long as I know what I defined X to be within my ice table, I can now potentially answer my question. The question that we're putting here is how much did copper chloride dissolve? Well, how much copper chloride dissolved? 5.8 times 10 to the negative 4th moles of copper chloride dissolved in 1 liter of solution. Ta-da! Magic, right? You're not supposed to say, yes, that was magic. That wasn't magic. Just for the record. Questions? Yes?
Since KSP only includes copper ion and chloride ion, do we necessarily have to do the ice table, or can we just assume that all of it is transferred?
So really the question that you're asking is, do you ever need to do an ice table?
For this specific situation?
Do you ever need to do an ice table is actually what you asked.
No.
No. You never need to do an ice table. Why do we do an ice table? Clarity, that's it. It's to organize your logical flow of what happened to those individual concentrations and species, where you're putting individual variables so that you understand what's going on. If we're talking about molar solubility, okay, is this a straight up forward enough expression that you think you could do it without an ice table? Okay, that's a personal question, believe it or not. Okay, if you feel you can, Bob's your uncle, go for it. Okay, if you don't think you can, we're going to draw it out. Right? That's how you should set it up. This provides the context that allows you to organize your thought flow so that you can get to the correct answer. Okay? Are there ways that we can convolute and make this more confusing or challenging that might require the need of an ice table? Yeah, there are ways. It'd be really dramatic if this was true. I don't know if it's going to work. Ta-da! Have fun. Set it up. So we're going to look at this in two different ways. We're going to do it the way that the vast majority of you are setting this up, and then I'm going to show you a slightly different method that usually causes people to panic and freak out a little bit, but it still works. And so it's going to depend on what you're being asked for an individual question to manipulate. Where most people went through and did is they went through and said that we're starting with some X value of calcium fluoride that needs to dissolve, which means the change is going to be minus X. The calcium ion will be plus X. What's the fluoride? Plus 2X. I have to take into consideration that I'm producing 2 fluoride for every 1 of the calcium fluoride. That's why we have that 2 from our expression. Okay? We could pull that all the way down into our equilibrium and repeat that, but here's the next part that we want to deal. What's the concentration of our calcium ion? X. I'm going to use parentheses to represent the concentration of the calcium ion. What's the concentration for the fluoride ion? Which means when I go through to solve this, this isn't divide by 2, this is divide by 4 if you're grouping your terms. You have to make sure that that square affects the 2. That's where your parentheses are. You have to make sure you don't accidentally drop that out. Does that make sense? Okay. So I said there was another way to go through and do this, so let's go through and do it. Okay. Most people are like, why would you go through and do this? It's so much extra confusing. It's going to depend on what you're being asked. Okay? So if we go through, we've got our ice table. Okay? I start with 0 calcium, 0 fluoride. Well, what's going to happen to the fluoride concentration through the course of this reaction? It's going to increase, so it's going to go up. What is it going to go up by? Well, I don't know, so I'm going to call it X. What's going to happen to the calcium ion concentration? It's going to go up as well, but now it's not going to go up by X, it's going to go up by 1/2 X. Okay? My change over here is going to go down by 1/2 X. That's still going to come out to be 0, which ultimately isn't going to matter. We're going to get 1/2 X here, we'll get X here, which means when I now go through to solve my expression, my calcium ion is 1/2 X. My fluoride concentration is X squared. And when I go through to solve this, am I going to get the same X as you all did? No. Does that mean I'm wrong? No. And one of the important questions that you have to address, which is what we addressed in the last solve that we went through, is what did we say X was? In the solve that we had initially written up that you all more than likely did, you said X was the amount of calcium ion and the amount of calcium fluoride that dissolved. Right? What did I say X was? The fluoride ion. Which means if I'm now going through to answer the question that's asked of me, X is not correct because that's not what I needed to solve for. What did I need to solve for? 1/2 that value. And when I solve for now 1/2 that value, what do I get? The exact same answer that y'all got when you solved for your quote-unquote X. So why would we set up the question differently? Why would I go through and choose to have X be fluoride versus X be the calcium fluoride? It's going to depend on the question asked. If the question asks for calculate the molar solubility of calcium fluoride, what do you want your X to be? Calcium fluoride. Keep it as straightforward and simple as possible. But what if the expression said calculate the concentration of fluoride? If it's going to say what's the concentration of fluoride, what do I want X to be? I want my X to be the fluoride, because it's going to simplify how I go through and run my calculations at the end. So when you start dealing with these calculations, you have to decide what your X means. That's the point of the ICE table. You just have to realize that there's units tied into it as you navigate it. Kind of make sense? And as you navigate molar solubilities, one of the things that is frequently going to change is those coefficients, which is going to potentially change your ice table from somebody else's, because maybe they're solving for a different piece of that ice table. Kind of get it? Okay. Isn't mathematics fun? Okay. So what if there's ions already in the solution? Okay. So for this previous question, we've made kind of a big assumption. What we assumed was that this was deionized water. We assumed there was nothing else in there, so the only things going in would be the calcium and the fluoride. Okay? And in studying scientific reactions, more than likely, that's what we would choose, right? Because we now control the variables. Why would we ever look at a situation or run an experiment where we didn't control the variables of our water? Well, what do you want to study? Maybe you want to study the solubility of calcium carbonate in pond water versus ocean water. Why would you study that? Because each of those ecosystems use calcium carbonate differently, and those ecosystems are going to have different ions in place. Those different ions could affect the solubility of my calcium carbonate. So I'm going to want to understand what's happening in the actual world and how that actual world can have an effect on what I'm observing. I don't want absolute grand truths if those absolute grand truths never apply to the reality that I'm working with. Right? So what we'll encounter is a system of real-world stuff. Okay? Why does this become particularly important? We can look at a map of water hardness across the states. Okay? And you'll note that every single one of these has hard water. Okay? There are always ions dissolved in our water. Those ion concentrations will change how we interact with our environment. For instance, if we go into, say, South Carolina. South Carolina has slightly hard water. If we look at their taps, we're probably not going to see that center picture. But if we go through and look at, what is that state? Utah? Did I do that right? Is this one? Is that one Utah?
Yes, Utah.
Cool, look at that. Yes. Okay, I know my geography. I shouldn't have been proud of that. Okay, if that's Utah, okay, what are our taps probably going to look like? Probably like that. Unless that particular household has a ton of money, and what do? They remove all the ions before it makes it into their household. Okay? That costs money to be able to manipulate those things. So if we're looking at potentially even cost of living, the cost of living of dealing with our water in, South Carolina is going to be a lot different than the cost of living of dealing with our water in Utah. Okay? How much different? That's going to determine all the costs and relative prices, and I don't know that. Okay, so let's take a look. Okay, we still got our same expression, our calcium fluoride, right? That's the one we looked at. We did calcium fluoride. Okay, we're not quantifying it yet. At this point, all we want to say is if we use hard water, we have other ions present. One of those ions that is very commonly found in our water is calcium. So what happens to the solubility of calcium fluoride if we increase the concentration of calcium? Blue box, talk. Okay. It says to write the KSP expression. I think that was a direction for the instructor, but if we wrote out our KSP expression, we get calcium plus 2. Our fluoride, right, squared. We already had all that. Okay. I would argue we don't need that, but we could use it. Okay, what this question is saying is what happens if I increase the concentration of our calcium ion? If I increase the concentration of calcium ion, what is that going to do to my equilibrium? Shift it to the left. What does that mean about the ability for my calcium fluoride to dissolve? decreases its ability to dissolve. So if I increase the calcium ion, I decrease the ability for it to dissolve. What are we using to come up with that analysis? Frenchman. I'm not going to repeat your pronunciation, but Le Chatelier, okay, is our pronunciation theoretically, or at least a less dangerous sounding one for a recording. Okay. That's all we're using to manipulate this. Could we do something else to figure this out? Yeah, why not? You know what else we could do? Okay. For the record, this is known as the common ion effect. What we're doing is adding an ion that is common or has something common about the overall expression we're studying. Okay. If we don't want to go through and deal with Le Chatelier, what could we do? Math. Okay. In theory, you all came up with an x value from the last question, so we'll backtrack real quickly. When we looked at this question, you had a k, right? Or sorry, an x. Okay. Hold on to that number in your head for a second. Whoop, one more. Come on. Okay. With no, we'll say without calcium ion present, what was your x?
Or CaF2.
Yeah. I'm not doing a string of zeros. 2.14? Okay. And you said 10 to the negative 3?
4.
You said 4. Okay, he said 4, so I think it's more than 2 zeros. You should check your work. 2.14 times 10 to the negative 4? Okay. That was our molar solubility with 0 calcium ions present. So what do you got to do now? We got to figure out what happens if we have calcium ions present. Okay, do you need an ice table? Again, I would argue no, but the ice table can help us to organize our logical flow. Okay, our initial conditions, we're talking about some amount of calcium fluoride that dissolves, so we could pick that with X. What would be our initial concentration of fluoride? Cool, good answer, 0. We didn't have any fluoride. Okay, how about calcium ion? We do. We do have some calcium ion present. We have 0.2 molar concentration. What happens when we move into our change? Since I still have 0 fluoride, what's going to happen? The fluoride ion is going to have to increase. What's my calcium ion going to do? If the fluoride ion goes up, what must the calcium ion also do? It also has to increase. We don't have a choice there. So all I'm including is the signs on these first. What's going to happen to my calcium fluoride? It's going to decrease. Because I'm trying to figure out the molar solubility, now I can go through and try and deal with my x's. How much do I want my calcium fluoride to decrease? I want it to decrease by x. Because I want to solve for that molar solubility. I want to keep this as straightforward as possible. How much does my calcium ion increase by? X. How much does my fluoride ion increase by? 2x, because we're taking into consideration that factor. What's our equilibrium concentration? Our equilibrium concentration of our calcium fluoride will be 0. The calcium ion, I don't know why I decided to change the color there. 0.2 plus x, and then 2x. We can go through and set up my K expression. 0.2 plus x times 2x. Sorry, I started to do the calculation in my head. Times 2x squared. What does this have to equal? The KSP, which was conveniently written there for us, 3.9 times 10 to the negative 11th. Right? Because we have fancy calculators, what could we do? We could immediately plug this into our calculator and have it go through and solve for our x value. How many x values are we going to get? Fair play. I didn't look at it right. We'll get. Do we get 3? Is that how it works? I honestly don't know.
I mean, I think one of those would be
Okay, if you have a I honestly don't know the mathematics on that, but it is a cubic. So we're going to get more than one value. What you would have to go through and do is decide which value made the most sense, okay, when you went through and solved that. Okay, so you could do your cubic system, figure all that out, okay, and have it solved, but that means trying to solve a cubic. Okay, when we solve a quadratic, what do we have? A quadratic formula, right? Is there another way we could do this without doing a fancy cubic solve? How big do you think x is going to be? Say again?
Small.
Really, really, really small. So what's 0.2 plus a really, really, really small number? It's not a really, really small number. It's 0.02 or 0.2, sorry. Okay? Like if I want to lose weight and I just pluck a hair out of my head, I've officially lost weight. Does that count as losing any weight? Okay, a single piece of hair relative to my body mass is irrelevant. Okay, the same thing is going to happen here. So you could make an assumption that x is really, really, really small, which means you could then change your calculation to be 0.2 times 4x squared. Note where I've shifted the parentheses now. Okay, and now you could just go through and solve it as the square. That simplifies our calculation significantly. At the end, what do we get for an x value?
6.98%.
Can I get a second on that? Going once, twice. Okay, we're just going to assume that that was valid. What does that mean happened to our x value? What happened to our x value when we added calcium, going from red to blue? Did the blue value get bigger or smaller? It got smaller, which means less calcium fluoride dissolved. Isn't that exactly what we said using Le Chatelier? Yes, it is. So we can go through and actually quantify and see that differential, or we can approximate it. Why would we choose one versus the other? What does the question ask you to do? If the question is just asking which direction does it go, up or down, you can just say up or down. Okay? If it's asking for a quantified difference, then you need to run through your calculations. Make sense? Questions? Okay. Which then is going to take us back to our acid-base chemistry, which is a little bit odd. So let's actually hold on that. Let's not quantify it, but let's look at other things that we could do to play around with this system. So we said we could go through and increase the calcium ion concentration. Okay, could we increase the fluoride ion concentration? Yes. How do you increase the calcium ion? You just have calcium ion there. Okay, how could I increase the fluoride concentration? I just put fluoride in there before I start my dissolving process. So it's fine to increase those values. Could we decrease them? That becomes a challenging question, because if we were to go through and look at this reaction, and if we looked at our initial concentrations, what were the initial concentration of our calcium ion and our fluoride ion? 0 and 0 if we're looking at pure water. We said we could increase it by adding calcium ion in. That's what our initial question said up at the top. What I'm asking is, can you decrease it? You're like, no, there's no way you could decrease that concentration. Sort of. What happens if I add an acid? If I add an acid, what am I talking about? What do acids do? Okay, the quiz is next week, for the record, remember. If we talked about an acid, HCl plus water, what did the acid do? Did it take the hydrogen? Okay. The acid supplied a hydrogen, supplied H+. So it increased the concentration of H3O+. The net result, if we're looking at that change, is really just the donation of H+. It donated H+ to this guy, which is what gets us to this guy. Yeah? So if I'm talking about adding an acid to this reaction, what do you think that acid, and so our acid is just H+, what do you think that H+ might interact with? I like your answer, sort of. It's not fluorine, it's fluoride. Okay, what's the difference between fluorine and fluoride? Ide, what does the ide mean? Are we in it, right? Okay. Negatively charged. So why are you saying the H+ should interact with the fluoride? Chemistry likes to cancel charges. So that H+ could interact with that fluoride to make what? HF. Okay. If this reaction happens, what happens to the concentration of fluoride? It goes down. So by adding acid, I can reduce the concentration of fluoride. What does that mean about the solubility of my calcium fluoride? If I decrease the fluoride, the equilibrium shifts to make more, which means this dissolves more. Okay? So I can change the pH of my solution. Another fancy way of saying we're increasing H+, and that H+ could react with the fluoride to make HF, and that decreases the concentration of fluoride. But we are making an important assumption there, and we're going to come back to that in a second. First, I wanted to hear your question.
Can acid react with any negatively charged?
Can it react with any negatively charged atom? No. Okay, so let's do a quick modification to this equation. I'm going to still keep this. So we'll say plus H plus goes to HF. What if we looked at the solubility of calcium chloride? Would I get the same effect here? Yeah, absolutely. You would decrease the concentration of chloride in this bottom case, just like we decreased the concentration of fluoride. Okay? And in that statement, unfortunately, we're wrong. Why are we wrong? Okay? This has to do with the assumption that we're making. When we add the H plus into the system, we're making the assumption that that direction towards HF is a valid direction to happen. What determines whether it goes towards HF versus goes the reverse? We're now talking about equilibrium, and that would be the equilibrium that is dictated based off of our... If you're like, well, I don't really know, let's talk about what that reverse reaction would look like. That would be the K of our F minus, well, I don't know why I wrote 2 there. Our F minus times our concentration of H plus, because all we're concerned about now is right here, divided by HF. What does that expression look like? It's a tricky expression. That's showing H plus, also known as, particularly in a water environment, H3O plus, which means what are we looking at here? This isn't just a general K, this is the Ka. That Ka is going to dictate the directionality of that reaction. And as long as that Ka is not massive, what happens? I'm going to produce a significant amount of HF. Okay? And if I produce a significant amount of HF, the concentration of fluoride ion decreases. Why does that matter when we move now to the second reaction? What's happening here? Well, the Ka, very similarly, I don't know why I decided to invert it, but our H plus, our Cl minus over HCl. Do you know the Ka for either of these two? People are like, no, nope, I don't. Should you? Yes. We've actually defined the Ka for one of these. We defined the Ka for HCl. What did we define the Ka for HCl to be? It's a strong acid, and because it is a strong acid, what is its Ka?
Whatever the concentration is.
Massive, which means that reaction only goes towards the reactants. So if I'm looking at the solubility of calcium chloride, changing H plus concentration has no effect on the solubility because I'm not able to remove the chloride concentration by adding H plus. So I have to know something about the Kas for those individual species. Okay? And you're like, but I don't know the Ka for HF. You're right, you don't. But you do know that it's not a strong acid because someone said it would be a really good idea to have that information handy so that you could answer a question like this. What would you do on an exam or a quiz? No clue. Sorry. Don't know yet. Okay. What would you do on the homework? Look up the Kas. If your Ka is massive, that reaction isn't happening, which means you're not changing the concentration of whatever ion you're playing with. Okay? If it's not one of the strong acids, you now know that it will play with or change that concentration. How much, the magnitude of it isn't super critical, but recognizing that it does change is what we need to realize. Kind of, sort of? Why does this matter? Okay, well, this matters because of that picture that was just up on the screen just a half second ago, right? That matters because of this. We're talking about acid-base chemistry. Acid-base chemistry can be incorporated into our solubility chemistry. Well, why would that matter? What is this a picture of? Bleached coral. Why is the coral bleached? Why did the acidification of the ocean cause it to bleach? What makes the structure of coral? Calcium carbonate. And when you increase the concentration of hydrogen ions, guess what happens to the solubility of calcium carbonate? It increases, which means any creature that relies on calcium carbonate being a solid is now screwed because by changing the pH, you've now dissolved their ability to exist. That's very problematic. Okay? So, climate change, CO2, this is something that is happening. This is not something that is deniable. We can see the concentration of CO2 change drastically. We can also study the fact that when we have CO2 in the presence of water, it reacts to form carbonic acid, H2CO3. Okay? So the more CO2 you have in the air, the more it dissolves into the water. The more it dissolves into the water, the more it reacts with water to form carbonic acid. Carbonic acid is fun because it will also react with water to form H3O+, which means we end up decreasing the pH of our ocean. As we decrease the pH of the ocean, we're making it more acidic, and that acidity can now have secondary effects or knock-on effects for our solubilities. Okay? So as we continue to increase CO2, what happens to the pH of our water? It continues to decrease. Okay? And this isn't just, random scientists saying, well, maybe this can happen. We can directly observe this, ignore that. Here, atmospheric CO2, we can track the atmospheric CO2 increasing over time. Okay? We can then also track how much CO2 dissolved in the water, also increasing. Okay? Which makes sense. If you have more oxygen there, or more air, it's going to dissolve in more. And as it dissolves in more, what happened to the pH? That line is going down because you're talking about the increasing hydrogen ion concentration. Okay? So it is all directly correlated. We have direct evidence of this. where people start to get into, as far as I can tell, the debates against this. They aren't really debates. They're, the Earth is a big system, right? And we can mess it up, and the Earth will continue on. Just we won't. That's your argument? The argument is the Earth is still going to exist, but we don't. I want to exist. Why am I creating a system that prevents me from existing? That's a dumb argument, okay? Bar none, okay? There are other arguments that could potentially come out, but that's the most common argument. Well, the Earth's going to be fine. Fuck you, the Earth's going to be fine. How about me? Okay? So, calcium carbonate is only slightly soluble in water. That's why we have crustaceans. I don't know if that's the right word, but I'm just going to call them crustaceans. They use that as their exoskeletons, so we can look at mussels. We can look at any kind of shell organism. We can look at corals. They're all using calcium carbonate to create their structure. Right? So if we look at its solubility, it's very, very, very low. That's why we're getting a KSP that's wicked, wicked small. Okay? This would be the KSP. Actually, now I'm going to think about it. I think that's representing the KSP in actual ocean water. If we go through and look at pure water, the solubility increases significantly, right? Why? Because ocean water is basic. Okay? That's going to change how our carbonate actually dissolves in. How do you know it's basic? Well, we could cheat. Look at the slides. What's the pH of our seawater? It's in the 8 range. That's over 7, so we're looking at a basic environment. As we continue to make it more and more acidic or closer to that deionized state, we start increasing the solubility. Okay? Literally what we're doing is saying, screw you, sea life. You don't get a skeleton anymore. That's rude. Okay? So if we go through and look at carbonate, carbonate is that negative charge, just like our fluoride. And if carbonate is a weak base, what's going to potentially happen when we throw in H+? So here's our calcium carbonate going to our calcium ion plus our carbonate ion. If I throw in H+, that plus and minus is going to hook up. As that plus and minus hooks up, what happens? I form HCO3 minus, and I could continue to push that to other things if I really wanted to. But ultimately, that structure is not a strong acid. How do I know it's not a strong acid? Because when your current teacher said that you should memorize what your strong acids are, this was not one of them. Okay, that would be a good place to do it. Okay, since I know that's not a strong acid, what happens to the concentration of carbonate? It will decrease as I increase the H+ concentration. If that decreases, what happens to the equilibrium of our poor seashells? Shifts to dissolve more to replace that carbonate. As that dissolves more, there goes the shell structure, right? And therefore their existence. Yeah? If it was a strong acid, what does that mean happens with this black arrow? Okay, for the sake of the recording. If this is a strong acid, what does that mean it does? It completely dissociates into the ions. Where are the ions? Up here. So strong acids, it's not even an increase in the products. It just, H+ has no effect on its concentration because you're making the statement that this exists. This is only existing because it's reacting H+ with the carbonate. Okay? So what we're doing is saying, how does H+ affect that reaction? If this was a strong acid, it doesn't, because I can't form the strong acid. It by definition goes back the other way. Okay? This is talking about H+ concentration. Are there other things other than acids? There are bases, and what do bases supply? Hydroxide. Hydroxide's a negative charge. What could hydroxide partner up with? Any of the positives. Okay? So what we're talking about with the common ion effect is not just does the ion appear in my overall KSP expression. but also how does H plus or OH minus affect those concentrations? Okay? That's what we're looking at within KSP. Okay? I am aware that we're done. I just want to talk through something else to be aware of as we navigate. Okay? With the quiz being on Thursday, okay, I'm a little panicked looking through at the slides because of this. This expression is actually a very, very important expression. Shows up through 152, it shows up in OChem, and it shows up in biochem for anybody that has to go through any of those classes. It's known as the Henderson-Hasselbalch expression. It's what relates a lot of these common things to each other. It helps to explain buffers. If you're doing anything with medicine, okay, how you get CO2 from your muscles to your lungs, okay, how do you get oxygen from your lungs to your muscles? All of that is navigating through something known as the Henderson-Hasselbalch. How do we ensure that the pH in our bloodstream stays constant? Henderson-Hasselbalch. Okay, is it helping to explain what's going on with that? That is a really massive concept, and I'm really nervous because we're talking about that literally 2 days before your quiz. Okay? That probably also means it's going to show up like crazy in the Alex homework. Okay? So if you've got questions, please direct them to me so that I can try and help you get the context to figure out what's going on with that. We'll talk about that stuff next week. The rest of it is ultimately just kind of examples of things that we would navigate through.